Okay. Hi there. My name is Matt Layher.
And I'm Ganesh, and I maintain the storage engine of Prometheus.
And I work mostly on the node exporter. Welcome to the Prometheus introduction session. So it's worth noting this is the intro. We're going to have the Prometheus deep dive tomorrow morning, I believe. So if you have questions about more advanced aspects of Prometheus, please join us there. And also, we'd like to give a special shout out to Julius Volz, one of the co-creators of Prometheus, for his help with the slides. So first, what exactly is Prometheus? Prometheus is a metrics-based monitoring and alerting stack. It is an entire ecosystem of components. So for example, you have things like our instrumentation libraries. The Prometheus client can be exposed from several different languages, such as, for example, Go, Python, Java, Ruby, C, Rust, all kinds of different things. And there are also Prometheus exporters, and those operate in slightly different ways. So the Prometheus server itself is your metrics collection and storage system. Actually gathers time series and stores them in its database. And then once you have that data, you can make use of it by querying Prometheus, creating alerts. So for example, if you'd like to know when you've reached a certain level of memory pressure, or if your disk space is about to run out, you can do that. And also we support dashboarding via the Prometheus API using software such as Grafana. But what's cool about Prometheus is it's really meant for all levels of your stack. So not only can you use Prometheus for your own applications, you can instrument things like the Linux kernel or web servers like Apache, Nginx, and etc. Finally, Prometheus is made for dynamic cloud environments. So lots of folks deploy Prometheus with things like Kubernetes, but that being said, it's also very useful for the home user as well. So in fact, I run Prometheus at home just for monitoring my home services, and I actually have like alerting set up to my phone, so if something goes down, I get notified about it. So you can run it in production, but it's also a lot of fun to use at home. So Prometheus is a lot of things, but there are certain things that are out of scope for the project. So for example, Prometheus does not focus on logging or tracing. These are different observability primitives, and while they are quite useful, Prometheus is squarely focused on metrics collection. In addition, Prometheus does not provide automated anomaly detection on its own. So for example, you could gather data with Prometheus and then feed that into a different system to do things like anomaly detection, but Prometheus does not feature this built in. Finally, the Prometheus server stores all of its data to a local disk. It does not necessarily provide scalable or durable long-term storage. So if you want to store time series, for example, multiple years, that could get kind of problematic, but there are workarounds for this as well. So a little bit of the history of the project. The Prometheus project was originally created in 2012 at SoundCloud, designed to address some of the flaws in existing monitoring systems. The project became open source and was worked on for a couple of years before being fully publicized in 2015 on places like Hacker News. In 2016, we joined the CNCF as I believe the second project after Kubernetes, and then Prometheus version 1.0 was released. A year later, we released Prometheus version 2.0, and this was done primarily so we could replace the storage backend. So now we have a new storage backend called TSDB, or Time Series Database. So let's discuss the architecture of Prometheus and see how all the different components fit together. So first we have our targets, and these, for example, could be applications that you and your team are developing. So something like a web application, which could be written in something like, say, PHP or Ruby or Python, and like an API server written in Go or some other language. So these are targets you control, and as such, you can use the Prometheus client libraries to instrument your own applications. So we feature client libraries for languages such as Go, Java, Python, but there are also community bindings written for languages like Rust and C as well. However, not all of the software in your stack is necessarily something that you will control. So for example, you're probably deployed on a Linux virtual machine, you might be connecting to a MySQL server, you might want to look at the C group utilization or something on your machine. But this software does not necessarily expose native Prometheus metrics, so this is where Prometheus exporters come in. And an exporter's job is basically to query metrics from some source, such as MySQL, using that source's native interface, do some transformations on that data, and finally expose those metrics in the Prometheus format so that the Prometheus server can translate between that native format and then send the metrics up to itself. So here's an example of what happens when you expose Prometheus metrics. If you were looking at something like the /metrics endpoint on one of your instrumented services or one of the exporters, you might see a metric something like this. So there's a bit of metadata here that's helpful for humans and also indicates the type of the metric. But here we have a time series called HTTP requests total. There are a couple of labels here in between the brackets, and labels are how we partition data into different dimensions within Prometheus. So for example, we have the HTTP method, such as this metric was created by a post request, and then a couple of different status codes. So we can actually see which requests resulted in an HTTP 200 versus an HTTP 400. And finally, we have the value of the time series as well. So now you have your Prometheus server in the middle. Prometheus will, on regular basis, reach out to all these different targets, so your own applications as well as your exporters. But Prometheus needs to find a way to actually get a hold of these applications and figure out where they live. In order to do so, you can configure a static target list if you'd like. However, Prometheus also has built-in support for service discovery using mechanisms such as DNS. So for example, you can query an SRV record and get a list of targets for Prometheus to scrape. You could use the Kubernetes integration. So for example, if you have pods that are coming up and down at different intervals, Prometheus will notice that and create time series and also flush out stale time series for those pods. You can integrate with the service discovery of your cloud provider, something like AWS. And finally, we also have a custom service discovery hook. So if you and your team have some kind of in-house system or another way you'd like to manage service discovery, you can write out a file in a standard format. Prometheus will see that it has changed, read it in, and then can be integrated with your system. So once you're actually gathering this data at regular intervals and you have some time series being built up within Prometheus, you want to actually do something with that data. So Prometheus itself features a web UI, and the web UI is good for kind of experimenting and exploring with different queries. So it features kind of a basic interface that you can use. Ganesh will explain that a little bit more later, but it also shows things like the current configuration of the Prometheus server, the current targets that are loaded into memory and whether or not they are healthy, and also things such as the runtime flag configuration for Prometheus. If you want to do a more advanced use case, we recommend the use of software such as Grafana. And Grafana enables you to create persistent dashboards. So for example, you can do 10 or 12 different Prometheus queries at once and create a tactical dashboard for you and your team to help understand the health of your service. Finally, Prometheus also features an API. So for example, if you wanted to use something like an anomaly detection system, it could read data directly from Prometheus using this API, pull it in, and do whatever it would like. The last component of the Prometheus ecosystem is the alert manager. So for example, if you want to set up an alert in Prometheus that says, say, if I'm over 80% memory utilization on this machine, fire an alert, you can do that. And then if you configure Prometheus to reach out to an alert manager component, it will actually send a hook whenever that is firing. With Alert Manager, you can dispatch that alert to different locations. So say, for example, you're using something like PagerDuty, you can issue a page immediately. Or I actually use an app on my phone called Pushover for my home infrastructure, works just fine too. So some of the major selling points of Prometheus include the multi-dimensional data model. Because of the fact that you can have a time series with many different labels and then many different label values as well, you can really easily slice and dice your data into a lot of different dimensions and gain a lot of insight into what your applications are doing. Prometheus also features a very powerful query language we call PromQL. And it's a simple and efficient Go server. So Prometheus is a statically linked Go binary. If you really want to, you can just Go build or even cross-compile it, SCP it up to a Linux machine and just run it. And it will pretty much just work. Finally, since Prometheus supports things like service discovery, it's a great fit for applications that run on top of things like Kubernetes or are integrated with some other existing service discovery mechanism. So let's discuss a little bit about the Prometheus data model. So first, what exactly is a time series? You can think of it as an identifier. So for example, our HTTP request total time series, and then we have a vector here. And the vector contains some tuples. Each of these tuples contains a timestamp of when a sample was gathered and also a value. So for example, Prometheus will reach out at time equals 0 and collect some value, and then perhaps again at time equals 15, time equals 30, and so on, and form a time series. And it's worth noting that each combination of different labels actually produces a new time series within Prometheus. So here's an example time series. We have this HTTP request total. It's coming from a job called Nginx, and we have an instance label attached as well. So if you have multiple different Nginx servers, you can actually filter on whichever one you'd like to query or see all of them in aggregate by using something like PromQL. So the result of this provides a pretty flexible architecture. The Prometheus metrics are laid out in a flat namespace, so there is no hierarchy involved here. Everything is just a flat namespace with labels, and the dimensions are explicit because of the different label values. And now, in order to actually operate Prometheus and talk about it a bit more, I will hand over to Ganesh.
Thank you, Matt. So I'll be just going through some of the points which Matt already mentioned here. So let's talk about querying. We already have data in the Prometheus right now using the exporters and all the other applications. So let's see how we can get the data using the queries. Yeah, so PromQL is a new query language which was built with the Prometheus. And it's great for time series computations. I will be showing some examples, and it's not a SQL style querying language. So this is a very basic query. You are mentioning the metric name and then you are saying the no mount point should not be root. So this query gives you all the mount points which are using more than 100 gigabytes of space, and mount point is not root. And all the queries in Prometheus looks like a mathematical equation that you would write inside your code. And you can consider the metric name that I'm showing on the left side as A divided by 10 power 9, which is greater than 100, just show me them. And you get a result which matches node file system bytes total and the other labels associated with it. Yep. And let's take another example, which is a little more complex than the current one. This is to find the ratio of number of 500 failed requests in your system, which is aggregated by every path. If you want to find the ratio, it will be in the form of A divided by B. So the place of A is taken by the rate at which we are getting the 500 requests aggregated by path, so that we can get the 500 request errors per path. And we divide it by the total number of HTTP requests that you are getting, and hence we get the errors per path. But if we don't want it per path, we can just remove the by path in the query, and we can aggregate it over all the requests that we are getting for the errors. And going a little more into this, there is also histograms, and this query gives you what's the latency of 99% of the queries of the requests that we are getting. So these are just high-level examples. I'm not going inside the queries, what it actually happens. These are just examples that you can do with the query language. There are many more functions like average, sum over time, and linear prediction, and many such things. So yeah, we will be going more in depth in the deep dive session tomorrow. So I'm just scratching the surface here. Yeah, and Matt mentioned about the ad hoc querying that we have in the Prometheus UI. So we just give the query in the UI, and you have the list of time series that it matches and the value. And if you want to see the graph for that, you can see there is another tab, and when you just click, you get the graph for the queries that you run. And this is just ad hoc. It's not persistent. You have to run the query every time that you want to see. So if you want to have persistent dashboards, you can use Grafana. You can have panels with time ranges mentioned in them with the query that it has to run in the panels. And every time you open the Grafana dashboard, the panels will be the same. Obviously, the data will be different because the time changes. Yep. And now talking about the alerting. So the main alerting stays inside the Prometheus, where you define the alerting rules. This, we already saw the query, which is the ratio of 500 requests that we are getting. And just like the mathematical equation, to convert ratio to percentage, I just multiply it by 100. And if it's greater than 5, for example, if it's more than 5% of the total request, and there is something called for. So if this is returning some time series for like 5 minutes, which means we have more than 5% of error for 5 minutes, then send me an alert. And we can attach labels to that and some description with Go templating language. And when the alert fires, it has to send to some external service so that it can take care of the alerts. So that's where the alert manager comes into play. So the Prometheus has these rules, handles the alerts and pushes it to alert manager. And as Matt said, the alert manager takes care of sending it to different hooks like Slack or PagerDuty, etc. And about the operational simplicity, Prometheus is a single binary, and it just runs on your local host. It uses the local storage. It doesn't need any object store. And if you want to run it in high availability mode, you just run 2 Prometheus with the same config and scrape the same set of targets in both the Prometheus. So that if one Prometheus goes down, you have another Prometheus which is running. Obviously, the local storage are different for both of them. And yeah, efficiency. It's very easy to have a moderate setup of Prometheus, which can take more than 1 million samples per second and have millions of series. I have personally seen a Prometheus instance that can manage more than 10 million series on a single host. Yep. And it's good to keep few weeks to months of data in the Prometheus, but as you know, the disk is not reliable, so you don't want to run a Prometheus with a very high scale for to keep months of data. For that, we have something called remote storage. Prometheus has an endpoint called remote write, using which you can write the data from the Prometheus to some long-term storage solutions. These long-term storage solutions are not strongly a part of Prometheus. These are community projects. For example, Cortex and Thanos. There were introduction sessions for Cortex and Thanos. I hope you have visited that if you wanted the long-term storage. So I'm not going in depth about them. Yep. So you have option for long-term storage. And yeah, so Matt mentioned about service discovery. For example, Kubernetes, you have pods coming and going, and you might have thousands of pods, and you don't want to list the IP and port of all those pods in your config. So for that, we have something called service discovery to handle this dynamic environment, where it talks to the DNS server or any service discovery that you have in your system to know what should be present. For example, it will give a list of 100 pods that should be present. But by using the alerting rules, you can come to know which pods are not there, for example. Yeah, and using service discovery, you come to know where to pull the metrics from. And the service discovery also gives some metadata about the pods and other hosts that you have, which you can attach to the metrics that you're pulling during the scraping period. Yep. And Prometheus already has built-in service discovery support for AWS, Google, Kubernetes, DNS console, and lots of other stuff. And we guess more will be coming soon. Yep. And yeah, I would like to conclude here. I don't want to go too deep into all the Prometheus aspects, so you feel comfortable in this talk. If you want to get more in depth, I recommend you to attend the deep dive session tomorrow, or we have a Prometheus booth in the sponsor showcase area, where if you have any questions, you can just come talk to us. So we looked at the dimensional data model, like the label values. Each label value is like a dimension in the time series database. It's a powerful query language. It's just like mathematics. You can do anything that you want with it. It's simple and it's efficient. Yeah, it's very simple to run. It's a single binary, and the service discovery is what makes it beautiful. Yep. Thank you. So we have another Prometheus maintainer here, so we three will be answering your questions. And unluckily, we have just one mic. So if you think you're going to ask questions, I recommend you to come a little bit to the forward so that we can hear. I'll repeat the questions. You have any questions? Yep.
One of the things about having a time series database is that write amplification to the SSD can be a problem. What features do you have inside of your database?
Yeah. So his question was, one of the problem with time series database is the write amplification for SSDs. Like if you are doing too much writes, the SSD is going to wear out. Yeah, so that was a big problem with Prometheus 1.0, where we used to just randomly write the data to the disk, if I'm not wrong. And with Prometheus 2.0, we don't write the data as soon as it comes. We store it in the memory. And to reduce the write amplification, we write it in the size of page blocks, so that we don't write the entire block of SSD unnecessarily. And once we have written Prometheus has in-memory part and persistent part. And once we write the data to the persistent part, we don't modify it so that we don't have to write a lot. So there is something called compactions, which takes care of other stuff like joining the blocks. But yeah, we write it in chunks of SSD blocks so that we don't wear out the SSDs. Yeah, so that's why we have long-term storage, because if you are running at a higher scale, it's difficult to avoid that problem. Yeah.
There's another problem that's common in these time series databases, and that is to maintain a consistent stream of writes that's always available, like with a varying read load. Because you just don't know how many readers you're going to have. You don't know what to read. You don't know what to read loads going to be, but you know you have to write data all the time.
Yep. So his question was, you have to keep mind of how there'll be read load, constant read load, which is going to increase or something like that. Yeah, how do you maintain a constant write rate? Yeah. Yeah. Constant write rate, I can say it depends on the system capability. Like we saw, we can ingest millions of samples per second. So if you want to increase that, you need to have a faster CPU and a lot of RAM so that it can hold in the memory, but it will hit a bottleneck somewhere.
As the queries increase, does your write load drop? Does your write head drop?
I'm not exactly sure about that, but as your queries increase, the memory consumption increases because it has to store some stuff in the memory. So it's going to affect a bit, but I guess not much. Yeah. Any more questions? Yep, I'll just come over there to repeat the question. Yeah.
Prometheus avoids like duplicated, so it's querying the, like for example, any kind of web app for this starts every frequency.
Yeah.
How it's avoiding duplicate values that it gets from.
Yeah, so he's asking, like in Prometheus, we scrape an endpoint multiple times. So how do we avoid duplicate values? So if at a timestamp 0, you have a value of 10, and if at timestamp 10, you have a value of 10 again. So I would not say it's a duplicate value. It's just the value that's present at that particular timestamp. So you just store it. So when you look at the history, historical data, what you have, you can just say at this timestamp you have this value, and the other timestamp you have the same value. So it doesn't matter if it's duplicate. But yeah, in terms of compression, we take the delta compression. So if it's same, we take the delta and we just store 0, and we don't store 10 2 times. So that there we have the compression there. Any questions?
Yes,
Yeah.
The scheduling inside of Kubernetes, have folks been using Prometheus to kind of monitor how Kubernetes is scheduling resources? Or is that the kind of wrong approach?
I don't think I have an answer for that. Do you have? Like his question was, how do we monitor the scheduling of resources within the Kubernetes using Prometheus? Do you have answers?
I'm not exactly sure what you're fishing for, but there's Kube State Metrics, which is exporting a whole lot of Kubernetes metrics from your cluster. Then the kubelets export stuff, the API server exports stuff. So you can certainly check like how much resources you have left. The interesting thing, and that might go into what you're fishing for, is there's the auto scaling in Kubernetes there are adapters where you can use Prometheus to inform the auto scaling. So usually you do, the vanilla auto scaling is pretty vanilla, but you often want to do something like auto scale based on request or on CPU usage or on RAM usage or like on arbitrary things which your Prometheus server is actually giving you, and then you can loop back the Prometheus server into the scheduling decision, the auto scaling decision, sorry. So that's not exactly scheduling, but not sure. Is that going into the direction you were fishing for? Yeah, okay, so I'm pretty sure the scheduling decision itself, nobody has yet looped back Prometheus into that. It's only like auto scaling where Prometheus loops back. Perhaps that will happen one day.
Any more questions? Yep.
Yeah, so my question is about the Prometheus data storage. It looks like Prometheus is storing all the data in disk or the SSD. Then what if the part of Prometheus be rescheduled or restarted? Then how Prometheus achieves the data persistency? Is Prometheus using persistence volume or any other strategy? Yeah.
So it's up to your deployment that you use a persistent storage so that once you restart the Prometheus, you have the access to the same disk that you ran on. So I told we have a persistent part of the Prometheus and there is an in-memory part in the Prometheus. So whenever we get samples from the host, we write it to something called write-ahead logs, which is a fairly basic concept in the databases. So we also store it in the memory and we write it to the disk in the form of records, which we can replay later. And coming to your point, we also write it in the blocks of SSDs. And yeah, so if the Prometheus goes down and it comes back again, the persistent part of the Prometheus is still there on the disk, but the in-memory part, we can replay it using the write-ahead log that we write whenever we get the samples. So it's like replaying the events that happened in the Prometheus. And we have the in-memory part for 2 hours, and the remaining is on the disk. So when you restart, at max, you have to replay the data that was there in the in-memory part for 2 hours. So did that answer your question?
Actually, I understand that, but my question is, what if the pod be rescheduled or restarted? Then how can we guarantee that pod is still mounted to the disk or the volume?
Yeah. So that handling doesn't come under Prometheus exactly. You have to make sure that when Prometheus is rescheduled, you are attached to the same volume. You can, if you are using Kubernetes, I think you can do it using the stateful sets, where if you restart the Prometheus, you'll have the same identifiers and you'll have the same persistent volume attached to it. So you're going to have the same storage if you use stateful sets. Yep.
If you're running really large clusters with lots of data, you said running multiple Prometheuses would just do it in high availability and they'll just grab from the same thing. So that doesn't really help you with the, with scaling Prometheus. Is that not a problem in practice? I don't have really large clusters, so I'm just curious if you can speak to that at all.
Yeah, that will be a problem in actual practice if you have a very large scale. In that case, you can actually shard the Prometheus. For example, you don't scrape everything with a single Prometheus. You run multiple Prometheus and scrape part of it in both the multiple Prometheuses. Prometheus, yes. So yeah, but in that case, you will have a problem. How will you have a global view of all the Prometheus together? So in that case, you can do multiple things. One is something called Prometheus Federation, where you have where one Prometheus talks to another Prometheus, like it runs a query to another Prometheus and stores that data instead. So if you have multiple Prometheus, you can have a single Prometheus which talks to this Prometheus at a lower level and aggregates the data over that. That's like one-time storage of the metrics. But I mentioned Cortex and Thanos. So Thanos has multiple modules which you can run independently. So Thanos has a querier module, and you don't need to run the entire Thanos infrastructure. So I can just run a single querier module which will talk to this all the Prometheus instances, and you can have a global view by querying the querier module of the Thanos. So these are the 2 solutions that I know of. Yeah, he has a point.
Thanks, Bjorn.
Just saying, because this is a very frequently asked question, and some people formulate it as a statement or as a question. They say Prometheus doesn't scale, which, depending on the perspective you viewed it, is actually true. But this, what Ganesh just said about the sharding, you usually try to shard along dimensions so that you don't need that global view. Like where Prometheus was created at SoundCloud, we just had one Prometheus server per team, essentially. They could do whatever they want with their Prometheus server, and it would like be big enough for the team. And it happens almost never that you actually want to aggregate the HTTP requests from the one team with the one of the others. So you usually don't have that problem. So SoundCloud, I think to the current day, they have never used one of those like global views, permanent storage, whatever solutions, and they're fairly happy with that. And yeah, so arguably it kind of scales. There's another trickery you can do when you actually have one, like let's say you have 10,000 instances of the same service and you actually have to scrape it all, and then you could do like a sharding where like every Prometheus server scrapes every 10th instance and then do some aggregation trickery, but I really wouldn't go down that path. And it's in practice, I doubt it's necessary for 99.9% of you.
Can you talk about some of the security, like Authentication TLS, that you can do in Prometheus with the endpoints, so the endpoints just aren't exposing, they're just exposing an HTTP that just anyone can query?
I don't exactly have an answer for this. Do we support HTTPS for the exporters? Yeah.
I think it's being.
Okay, another FAQ, of course. So the original idea is kind of old style. We have our trusted private network and everybody can scrape everybody. It's all HTTP. And of course, that's kind of not acceptable anymore. So Prometheus as a server, it's ironic because the Prometheus server has actually the client part of the HTTP request and the monitored clients technically are HTTP servers exposing the metrics. So the server is perfectly happy to just use TLS and bearer tokens and whatever, like all those things. And Kubernetes, that's actually happening usually, right? So that works quite nicely. The problem is more the part of the who exposes metrics or even the API of the Prometheus server itself, because then you have to implement a TLS server with authentication and everything. And the lame answer of the Prometheus community was so far, yeah, just set up a reverse proxy. It's not our problem. Like we want to solve one problem and solve it well, Unix philosophy. But then people got upset that they always have to set up like sidecars for that. Like a good example is you have the node exporter. It's not called the node exporter. Like you want to expose metrics, let's say MySQL, right? So MySQL runs in a pod and then you run a sidecar for MySQL, which is the MySQL exporter, and then it exposes the metrics in unsecured HTTP. So you want now like Nginx sidecar to reverse proxy it for HTTPS. So you have the sidecar for the sidecar. And we even had an example at SoundCloud where the monitored thing was already a sidecar. So we had the sidecar for the sidecar for the sidecar, and then it gets ridiculous. So luckily, there's an effort ongoing where we want to implement like a reference implementation how we in the Prometheus community want server sockets to do TLS. And that's done for the node exporter right now. It's almost ready to merge, but that's true for like a month, right? So anyway, this is the experiment. And once we have one good way to do that, we want to push it everywhere through the ecosystem. And then you can still not do it and do your sidecar if you need something else, but at least you have some bottom line TLS implementation that is used throughout the ecosystem. So we're working on it.
So one alternative approach I've seen, certainly all exporters, there are efforts being made to add like TLS to the exporters and stuff. One alternative approach I have seen is if you have many exporters running on one machine, you bind all of them to a local host and you build some sort of proxy that aggregates all of them, and then that proxy has TLS or similar, and it will expose the metrics of everything on its own machine. So that way you have one sidecar that does TLS and stuff like that, or you can implement like, Let's Encrypt support in that proxy thing. I don't know if there are any open source implementations of that sort of thing, but that is one approach I have seen as well. Any more questions? All right, thank you very much.